Yeah, so the next equation we're going to look at is this Bernoulli equation. Very similar to the linear, but not quite. So the big difference here is this piece right here, okay? This y to the n. Take that off. If we just look at this right here, that's exactly what a first order linear differential equation would look like. And that's what we've already learned how to solve. Throw this extra y to the n on the end, and now it's no longer linear. So this is what we define as a Bernoulli equation. N can be any real number, okay, but we really don't look at what happens when n equals 0 or when n equals 1, because when n equals 0 or when n equals 1, we would actually have a linear equation still. Obviously, n equals 0, the y to the n wouldn't be there at all, and clearly linear. And if n equals 1, we could divide through, we could actually, sorry, not divide through, we can move this piece over to the other side with the other y to the first, setting it equal to 0, and you would still see that it would be linear. And there's no need to change anything of what we've already done when we talk about linear. But let's look at what happens when that n is not 0 or 1, but any other possible real number, and see how we would go about solving it. Well, the method of solving it is very similar to the linear method, except for to begin, we need to make a substitution. And once we make that substitution, then we'll be able to use our linear methods to solve this Bernoulli equation. Okay, so here, if y doesn't equal 0, if we assume y doesn't equal 0, we could rewrite the equation by dividing this y to the n that was on this one side of the equation by dividing it back through the equation. So essentially dividing everything through by y to the n, or we could say we multiplied by y to the negative n, giving us now these two terms. Okay. So with that, we would then look at saying, well, let's let w equal y to the 1 minus n. So whatever this is right here, after I push that y to the n back through the other way, whatever this term right here ends up looking like, y to whatever power, that's the substitution we're going to make. And we're going to say w, okay? Remember, n doesn't equal 0, n doesn't equal 1. So that's what we're going to let w equal. W is just a random variable, but let's say w, okay? So once we make that substitution, what we then have to do is figure out what dy dx would end up being. Because if y is coming out, dy dx also has to come out. Well, what we would do is we would say, all right, well, let's take the derivative of w with respect to x, okay? And realizing that y is a function of x, we would have to use implicit differentiation to do that. So we'd start by essentially using the power rule, pulling this power out to the front. We get 1 minus n. The new power would now be 1 less. So now it's just y to the negative n. And then obviously with implicit differentiation, you have to do dy dx. So using this, what we can do is we can solve for dy dx by moving these terms to the other side of the equation. Okay? In doing so, what we're going to do is we're going to rewrite this original equation where the dy dx is going to come out and be replaced with this from our substitution. The y to the 1 minus n is going to come out. It's going to be replaced with the w. And we're going to look at this equation now. Well, if you notice, these two are going to cancel. Okay? I could then multiply through by 1 minus n here and here, giving us this and this. And if you look at the equation that we're left with in this case, that equation is now linear, where w is the dependent variable. So we still have x as the independent variable, f of x. Remember, n is just a constant, so that's a constant, that's a constant. And so in terms of w and x, this is exactly the form of a linear equation. So then we would solve this for W using the methods that we learned to solve linear differential equations. And then when we're done, we're going to then use the substitution that we had to resubstitute back in and figure out what the substitution is in terms of y. Once we have that, we have the differential equation solved for the function y that we were looking for. So this substitution is what makes it all happen. So let's look at an example. So in this equation, we have to recognize first that it's Bernoulli, okay, because everything about it looks linear except for the y squared. Take that off and look at this remaining piece of the differential equation. It is set up to be linear. I have dy dx plus some function of x times y to the first equals a function of x here, except for now I also have this y squared. So this is Bernoulli. So the first step of Bernoulli, what we're going to do is we're going to push this y squared through the other way in the equation. So divide everything through by y squared. Or you could also say we're going to multiply by y to the negative 2. So that will give us y to the negative 2 dy dx plus 1 over x y to the negative 1 equals x. And so this is where our substitution comes into play, right there. Whatever that is, that's going to be what w equals. So let's let w equal y to the negative 1. dw dx is going to equal negative y to the negative 2 times dy dx. Again, that's through implicit differentiation, treating y like it's a function of x. If you then solve for dy dx, so we can substitute the dy dx out, we would have to then move this negative y to the negative 2 over to the other side. So we get negative y squared dw dx equals dy dx. So that substitution we're going to need, that substitution we're going to need. So throw those things into this equation, and what do you get? Well, you're going to get y to the negative 2 times dy dx, but dy dx is negative y squared dw dx plus 1 over x times w equals x. So this and this will cancel. I would just have to move this negative through the equation to put it in its standard form for linear. So then I would get dw dx minus 1 over x w equals negative x. And now I'm ready to solve this linear equation in terms of w. So we're going to get our mu, right? Our mu of x is going to be e to the integral of negative 1 over x dx, which is real easy. So e to the negative ln of x. We simplify that, we get x to the negative 1, bring the negative in as a power, cancel the e in the log. So there's our mu. So we know we can skip to the step where we have the derivative of y times mu, or in this case, not y, w times mu equals f of x times mu of x. And so then we're going to integrate both sides. So we get w x to the negative 1 equals the integral of, well, look at this, x to the first, x to the negative 1, that's just negative 1 dx. So we have w equals x, so not that, w x to the negative 1 equals negative x plus c. Multiply everything through by x to get rid of this x to the negative 1, and we get w equals negative x squared plus cx. Now that's w. Our substitution was that w equals y to the negative 1, or we could say that w equals 1 over y. Well, if w equals 1 over y, then what we know is that y equals 1 over w. So I could say that this equals 1 over y, or even better, what I could say is that y equals 1 over w, so 1 over negative x squared plus cx. And so there's my solution to the Bernoulli equation. All right, here we have another Bernoulli for the exact same reason. Notice y squared over here. Aside from that, all the rest of this is set up just like a linear first order would look. In this case, though, with a y squared changes things. So it's not linear first order, it's a Bernoulli with that y squared. So what we're going to do here is we're going to push this y squared through the other way. We're going to get y to the negative 2 dy dx plus y to the negative 1 equals e to the x. Again, whatever's right here, that's our w. So w is going to equal y to the negative 1. dw dx would equal negative y to the negative 2 dy dx. This is exactly the same as the last one with our substitution. So then we could say that negative y squared dw dx equals dy dx. All right, so we got that, swap it out in the equation, and what do we end up with? What we end up with is y to the negative 2 times negative y squared dw dx plus w equals e to the x. Well, these two will cancel. Move this negative through. We get dw dx minus w equals negative e to the x. Now we have a linear. We look at our mu, which is simply just negative 1, which is e to the integral of negative 1 dx. So that gives me e to the negative x. So we skip to our steps of solving where we get d dx of w times mu equals f of x times mu. If you notice, these are going to cancel each other out. So then w e to the negative x equals the integral of negative 1 dx. So w equals negative x over e to the negative x, which we can also write as negative x e to the positive x. I missed out on a plus c here. Hold on. I'm going too fast. Missed out on the c. So let's do that again. W e to the negative x equals negative x plus c. Now move the e to the negative x. So w equals negative x e to the x plus c e to the x. Again, our substitution was all the way back here. So this is what 1 over y equals, or if we wanted to, we could say y equals 1 over negative x e to the x plus c e to the x. And there's the solution to your Bernoulli equation. As long as you know how to do this, which is your linear solution, then there's not much to this other than knowing what substitution to make. And the substitution to make should always be set right there once you push that y to a power through. Now, both examples used y squared to start with. That's not always going to be the case. I mean, we see a lot of those, but it's not going to be the case all the time. But the method is pretty similar to what we've already learned, so there's not a whole lot to this method other than recognizing the substitution that needs to happen. All right, so here we have another Bernoulli. A little bit more going on here, but it's still basically the same thing. We got this y squared here. It's not always going to be a y squared. The next example, I won't have a y squared there. The rest of this is linear, but not really a standard form linear because the x over here. So what I'm going to do is I'm going to push this y squared through this way. I'm going to push this x through that way. So divide by x, divide by y squared. And you see what we end up with is y to the negative 2 dy dx minus 1 plus x over x, y to the negative 1 equals 1. So here's your substitution. There's your w, same as the past two examples. W equals y to the negative 1. So that's going to tell me negative y squared dw dx equals dy dx. I'm just jumping straight to there because we've already done it twice. So then this is going to turn into y to the negative 2 times negative y squared dw dx minus 1 plus x over x times w equals 1. So this and this will cancel. We'll move this negative through, so this becomes a plus, this becomes a minus, and so we get dw dx plus 1 plus x over x, w equals negative 1. So here's our p of x, so then we look at our mu, where mu would be e to the integral of 1 plus x over x dx, which we can easily do. So we'll write this as e to the integral of 1 over x plus 1 dx. Just split this fraction apart. And so we end up with e to the log x plus x, which we could also write as e to the log x times e to the x. So adding in the exponent multiplies the bases. This one we can simplify to just be x. So we get x e to the x. Okay, so there is our mu. So once we have our mu, we jump to our linear steps. So we get this d dx of w times mu equals f of x, which in this case is negative 1, times mu. So now we got to integrate. So we're going to have w x e to the x equals the integral of negative x e to the x dx. So in order to do that integral, we need to do by parts. So u would be negative x, dv would be e to the x dx. So du would be negative dx, and v would be e to the x again. So we end up with w x e to the x equals u times v, so negative x e to the x, minus the integral of v du. So this has a minus already, so it becomes plus the integral of e to the x. So we end up with w x e to the x equals negative x e to the x plus e to the x plus c. So now we just divide this x e to the x through here to get w by itself. So we're going to end up getting negative 1 plus 1 over x plus c over x e to the x. We could do it that way. Another way I could do it is could have just not canceled at all, just straight divided this thing by x e to the x. So I could have also wrote this as w equals negative x e to the x plus e to the x plus c over x e to the x, which might be the better way to go because then we've done this a couple times. We got to resubstitute. Remember, w equals y to the negative 1 or 1 over y. If I want to figure out what y equals, I then have to flip this side. So there I flip this side as well, but by leaving it as one fraction, it's much easier to flip over. I can't flip over three separate fractions, but I can flip over the one. So x e to the x over negative x e to the x plus e to the x plus c. So there we go. There's our answer. All right, now we got to do one where we don't have a y squared here. And you see, it doesn't make a difference, right? Whatever y power is, it actually doesn't matter. So the fact that they were all y squared or that it changes doesn't change anything in terms of how you do the problem. So in looking at this next example, what you see here is we now have a y to the fourth. aside from the y to the fourth, everything else is basically ready to go, except for the 6. We probably should divide the 6. So what we'll do is we'll divide the y to the fourth this way. We'll divide the 6 this way. So we're going to have y to the negative 4 y prime. You also write as dy dx if you want. Minus 1/3 y to the negative 3 equals x over 6. So again, it's just dividing by the 6 and dividing by the y to the fourth. So if this is y to the first divided by y to the fourth, you get y to the negative 3. Well, again, that right there is my substitution. So I say w equals y to the negative 3 this time. So then dw dx is going to be negative 3y to the negative 4 dy dx. Well, dy dx, I have to then move this to the other side, is going to give me negative 1/3 y to the fourth dw dx equals dy dx. So there's my substitution for dy dx. Here's my substitution for w. Plug it into this differential equation. Remember, y prime is dy dx. So what I end up with is y to the negative 4 times negative 1/3 y to the positive 4 dw dx. That's my y prime. Minus 1/3 w equals x over 6. So this y to the negative 4 and this y to the fourth cancel. I'll multiply everything through by 3 to get rid of this third. So where am I now? W dx plus w equals x over 2. Again, multiply by 3, multiply by 3, multiply by 3. Or sorry, negative 3, because I could get rid of the negative as well. Which would then make this a negative here. Okay. All right, now I'm ready to go. P of x is 1, so mu is e to the integral of 1 dx, so e to the x. So then I get to the point where I have my derivative of w e to the x equals negative x over 2 e to the x. So now I integrate. W e to the x equals the integral of negative x over 2 e to the x dx, again by parts, just like we did the last example. So u equals, let's go negative x over 2 dv equals e to the x dx. So du would equal negative 1/2 dx, and v would be e to the x. So where are we? Let's move it over here. We get w e to the x equals u times v, so that's going to be negative x over 2 e to the x minus the integral of v du. With this minus, that turns into a plus, so we get 1/2 e to the x. So w e to the x equals negative x over 2 e to the x plus 1/2 e to the x plus c. Move the e to the x over, we get w. So w equals negative x e to the x plus e to the x plus c over 2 e to the x. So I divided by e to the x, but since these are also divided by 2, I just put the 2 in the denominator with it. And again, I could say this is c over 2 because it's a constant, doesn't really matter. So here's w. But now there's my substitution. Remember, w equals 1 over y cubed this time. So then this is what 1 over y cubed equals. And if that's what 1 over y cubed equals, then if I flip this side and I flip this side over here, I'll figure out what y cubed equals. So in the end, y cubed equals 2e to the x over x e to the x plus e to the x plus c. And so you see, it doesn't change anything. Y to the fourth, y squared. Your substitution is a different one. In this case, y to the negative 3 is my w. But the process of going through the problem is exactly the same. So this power is really doesn't change anything in terms of how we do the problem. So there's your Bernoulli equations, very similar to linear. If you have your linears down, these should be no problem. And so that takes care of the first order differential equations that we need for this first test.